Okay, hello everyone. Today actually we're going to be looking at complex analysis, and we have a lot of things under complex analysis, but we are just going to be starting with the definitions and some propositions under complex analysis. So with time we are going to look at more and more under complex analysis. So now looking at this now, this is the first video which I'll be making under complex analysis. So looking at this now, we're looking at the definition. You have what? A complex number is any number of the form a plus bi. You know that the a and the b are all belonging to real numbers, but you should know also that we have the real part and we have the complex part under complex analysis here. The a here is the real part, while the b is the what complex part. Now, and you know that I square obviously is what? Minus 1. So now you have this set in that form, which is what? A plus bi, such that a comma b belongs to what? R. So that's the set of what? Complex numbers. So you have a real part, you have an imaginary part. Now let's look at the visualization. Now looking at this plane, we have under geometric part, we want to look at just the geometric part of this. So under this, you know that we have the imaginary axis, we have the real axis. Do you get me now? And in real analysis you have just the x and the y, but in complex analysis we have the imaginary axis, which is more like the y axis, and we have the real axis, which is more than the x axis. You get now? So, and you have the theta, which is the polar form you have there. And you know that this is already self-explanatory, so I don't really need to do much on this. So this is how the graph, or this is how the back end of this is. So looking at this now, you have now moving to the next one, you have unary operations. That's just normal operations, just an introductory under what complex analysis. Do you get me now? So unary operation set. For example, now let's look at a set Z. We said a set Z belongs to a complex belongs to a complex set of numbers. So when it belongs to a complex set of numbers, you have what? A plus what? Bi. Do you get it now? So the a is the real part, and the b is what? The imaginary part. Do you get it now? The a is the real part because you have just a normal number, while the b, which is multiplying the I, would be the imaginary part. Do you get it now? So okay, now, and we also have what we call complex conjugate. Complex conjugate, these are some of the basic things which you are still going to be using under this course. Do you get it now? So complex conjugate, you have what? So complex conjugate is denoted with, you have z bar. Anytime you see z bar, you should know that it was complex conjugate. Do you get it now? And it's just like the opposite of the what? The set, which is a complex set you are dealing with. The complex set you are dealing with here, is a plus b I. So the conjugate is what? A minus bi. Do you get it now? So if you want to draw that in a graph, you have what? You have the x, the real part, and we have the imaginary part. But you have what? You have your bi, and which is what? The imaginary part, and you have your a, which is the real part. That's the what? Normal z, which will give us our z. Do you get it now? Which you have your polar form. But if you want to draw the negative side, which is the conjugate, you go to the negative of what? Imaginary, which is minus bi, and still the same a, just like what we have here and what we have here. So the graph of this is what we have on top, the graph of this is what we have below here. Do you get it now? And also the modulus of a complex number. You know that when you have something like this in real analysis, most of the times we call it, or in normal solving or whatever, most of the times you call it absolute, but you can also call it here, you call it what? Modulus inside what? Complex analysis. And you know that your modulus is what? Square root of what? A square plus b square. Do you get it now? So that's your what? Your modulus. So, and you should be able to draw that on a graph, because you have your what? Your a, and you have your what? B. This is your a, which is the real part, and this is your b, which is the imaginary part, which you meet as z, which is what? The square root of this. You know that this is your A, this is your B. Using Pythagoras theorem, you will get what? The hypotenuse, which is what? Square root of what? A square plus B square. So there are more ways of what? Understanding this, but this is just a normal logical way to get it. You get me? So now looking at binary operations on complex. So binary operation, we've talked about unary operations. Now let's look at binary operation on complex. Do you get it now? So binary, let's say you have Z, which is what? A plus bi, W, which is C plus di, and you also have what? You have addition. Let's say you want to add them together. You know that you add the what? Real parts together and you add the imaginary parts together. Do you get it now? So that you have AC plus what? BD, which is BI plus what? DI. If you factorize the I, you have what? B plus D all I. Do you get it now? So looking at this now, we want to look at the graph. This is how the graph looks like. Do you get me now? So you have what? You have the more like when you're adding vectors. When you're adding vectors, parallelogram of vectors. You know, like when you have a W and you have a Z and you want to add them together, more like bringing them to form a parallelogram. And this point we call it what? Z plus what? W. So not really Z bar W bar, but just Z plus W. Do you get me now? So because that two bars also means something else. So you know multiplication, just multiplying two vectors together. So now let's look at some proposition under this. Let's look at some proposition under this quick. So some proposition under what? Computer analysis, just the introduction. These are some of the things you will be needing and some of the things we will still be using in further things on this course. So looking at this now, for other topics on this course. Now looking at this, you have proposition 1, which is what? The modulus of z is equals to what? The square root of what? Z times z bar, and the z bar means what? The conjugate of z, which is the negative of what? Z. Do you get it now? So now you know that can also be written as what? Absolute value of z square equals to z times z bar. And now let's look at the proof of that. Now z equals to A plus bi and W equals to C plus di. Do you get now? No, these are all complex numbers. Do you get it? So now having this, let's look at the proof of this. Now let's prove that that is equals to that. Now let's look at square root of z times z bar. That's square root of what? What's our z? A plus bi. Our z bar is the conjugate, which is what? A minus what? Bi. Do you get it now? So knowing that already, now it will not be equals to what? Square root of what? A square plus b square. Why? Because when we expand this, a times a will give us a square. A times this will give us this. When I use this to multiply this and use this to multiply this, you know that they will cancel each other. Do you get it now? When I use a plus minus bi, it gives us minus a plus bi minus a bi rather, and bi plus a will give us a plus bi. You get that cancel that, and bi times bi minus I times I give us minus 1, and multiply by the minus, we have what? Ordinary b square. So which is square root of what? A square plus b square. You can try that for more clarification. So you see that it is a square plus a square is what? Is equals to the modulus of z, which is what? Correct. So we are going to prove that now. Looking at the next one, you have the 1 over z equals to the that's 1 over z equals to bar z, which is the conjugate of z over the modulus of z square. Do you get it now? So we want to prove that this is equal to this. Now when you bring this, let's look at the proof now. When you bring this to this side, you know this will multiply this, it will be equal to 1. Do you get it now? So you have what? Z. No, this z will multiply this. If you want to cross multiply, you have z times this, which is z times what? Then z bar over what? Absolute value of what? Z square, which will be equals to what? 1. Do you get it now? So z times z bar is what? Bringing it to this place, z times z bar is what? Absolute value of what? Z square. Do you get it now? So this will become absolute value of z square over what? Absolute value of z square, which will give us 1. So we'll be able to prove that correctly. So having known, you already know that now. Now let's look at another proposition, which is the third one. This one says the absolute value of the real side of z. You know the real side of z is ordinary a. Do you get it now? Is less than the absolute value of z. So what's the absolute value, which is same thing as modulus? The modulus of what? Real value, real side of z, which is what? The modulus of a, which is equals to square root of what? A square. Do you get it now? So less than or equals to the modulus of what? Z, which is square root of what? A square plus what? B square. So you should know that this will give us z. This is always less than this. So that has been proven. So now also, this is another important proposition which we might be using more often. So you have the real side of z is equals to 1 over 2 open bracket what? Z times the conjugate of what? Z. Do you get me now? So now let's look at this. Let's see if it's equal to each other. Now this one, now bringing this to this side, you have what? 1 over 2 what? What is our z? A plus bi plus what's the conjugate of z? A minus bi. Now multiplying this, you have what? Abi solving this, collecting like terms, you have what? This will cancel this. That bi will cancel minus bi. You have a plus a, which is 2a, 2a, 2 cancel 2, you have ordinary a. And ordinary a is what? The real side of what z, which is a. So that has been proven correctly. So you are still going to use this under triangular inequalities. So using this one also, solving this one also, you have what? For number 5, which is proposition 5, you have what? The conjugate, that's the product of zw conjugate, is equals to what? Z conjugate times what? W conjugate. It looks obviously true somehow, but we are going to prove it so that we can be sure of what we are doing. So now let's look at this. What's the conjugate of this? What's the conjugate of this? So which is the bar? What is z? What is z times w? You solve what? Z times w. So what is z times w? Z times w is this. When you multiply z and w is this, and this is z. Multiply them together, multiply the real everything, you get what you have here. Bringing the real together and the what? The complex side or the imaginary side together. So you have this. Do you get me now? So having gotten this, which you have a bar on top. So the bar of this means what? The conjugate of what? This. So that means this sign will change to what? Negative. Do you get it now? So the sign changes to negative at this point. Do you get it now? So that is for this. So let's check if this, let's check for this whether you get the same thing as this. So for this also, you have conjugate of z times conjugate of what? W. Conjugate of z to give us -1. Conjugate of w to give us -1. So multiplying that together also, you will still get the same thing as this. So that's how we proving that this is equals to what? This. Do you get now? So some of these propositions you will still be needed it in solving some questions and some things you want to do under this. So you just need to get familiar with them. So also you also have some few proposition here which you can do on your own also. This is more like easier. The imaginary part of z equals to this, and the conjugate of what? This is equals to what? That. So this is all for now. In the next video we'll be looking at triangular inequalities and some other things also. So I'm soft, and don't forget to like, subscribe and share this video. Thank you.